Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the deep story of how Earth's continents learned their ancient dance of drift. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 4.5 billion years ago, Earth exists as molten memory. The planet spins through space as a ball of liquid rock, glowing cherry red against the cosmic dark like an ember torn from some celestial forge. No continents drift, because no continents exist. No oceans stretch between landmasses, because water itself remains trapped as vapor in an atmosphere too hot for clouds, too violent for rain. The surface temperature hovers near 2,000 degrees Fahrenheit, hot enough to melt copper pennies into puddles, hot enough to turn the hardest granite into flowing rivers of luminous stone. The young world breathes heat into the vacuum of space, radiating infrared light like a planetary fever that will take hundreds of millions of years to break. Day and night mean nothing here. The entire surface glows with its own light, brighter than the hottest desert noon, painting the darkness of space with waves of thermal radiation that speak of a world still learning how to be solid. Asteroids and comets arrive like clockwork, each impact adding their ancient mass to the growing world with the methodical precision of cosmic construction workers. The late heavy bombardment continues its patient work of planetary assembly, delivering water locked in ice older than the solar system, carbon trapped in carbonaceous chondrite meteorites, and the raw materials that will someday become the Rocky Mountains and the Sahara Desert. Each collision releases energy equivalent to millions of nuclear weapons detonating simultaneously. Yet, the molten Earth absorbs these impacts with the magnificent indifference of deep time, swallowing asteroids the size of cities without so much as a ripple in its glowing surface. Only took 400 million years to build a planet. The universe whispers to itself with characteristic understatement. The bombardment delivers more than just mass and heat. It brings the very elements that will make continents possible. Aluminum and silicon arrive locked in stony meteorites, while rarer elements like potassium and uranium hitchhike along in trace amounts, destined to power radioactive decay for billions of years. Water arrives as ice, instantly vaporizing in the heat, but remaining in the atmosphere, waiting for cooler times. The chemistry of future continents assembles itself grain by grain, impact by impact, in a process so gradual that even geological time might grow impatient. Beneath the glowing surface, the first stirrings of convection begin their eternal dance. Denser materials sink toward the core while lighter elements rise, creating the earliest circulation patterns in Earth's interior that will persist in various forms until the sun dies. These currents flow with the infinite patience of geology, moving like honey through the semi-solid mantle at rates that make glaciers seem hasty. Iron and nickel descend to form the core, following gravity's inevitable summons, while silicate minerals float upward like cream rising in cosmic milk, carrying with them the chemical ingredients for future continents, future mountains, future valleys, where rivers will someday flow toward oceans not yet born. The planet sorts itself by density with the methodical thoroughness of a cosmic accountant, heavy elements falling inward toward the center, light materials climbing toward space where they will eventually cool into the first solid crust. This differentiation process operates according to principles so fundamental that similar sorting happens in every rocky planet across the galaxy, a universal law of planetary formation that makes Earth's story both utterly unique and completely inevitable. Scientists still debate whether this early Earth retained any solid crust at all during the Hadean Eon, or whether the entire surface remained liquid for millions upon millions of years. Some computer models suggest that cooling happened faster than once believed, allowing thin patches of solid rock to form and reform like scum on the surface of boiling soup, only to be destroyed by the next large impact and reformed again in an endless cycle of creation and destruction. Others propose that the molten magma ocean persisted much longer, stirred continuously by impacts and heated from below by radioactive decay until the bombardment finally slowed enough to allow permanent cooling. The truth remains locked in rocks too ancient to survive, destroyed and recycled countless times by the very processes they might have recorded. This uncertainty itself becomes a kind of poetry. The earliest chapter of Earth's story exists more as scientific inference than historical fact, requiring researchers to reconstruct the planet's infancy from isotopic clues and meteorite chemistry, like archaeologists of deep time working with evidence written in the language of atoms. Even the length of Earth's day remains uncertain during this period. The Moon orbits much closer than it does now, probably completing its circuit in less than a week, raising enormous tides in the magma ocean that would dwarf anything imaginable in liquid water. These tidal forces slow Earth's rotation through gravitational friction, gradually lengthening the day from perhaps 6 hours to something approaching our familiar 24. The planet spins faster than a figure skater pulling in their arms, making each Hadean day pass in a blur of molten light. In the darkness between worlds, Earth glows like an ember cooling in the cosmic night, neither fully formed nor entirely molten, existing in that liminal state between birth and becoming. The first hint of what will become continental drift lies hidden in these early convection cells, already establishing the deep circulation patterns that will someday carry continents across the globe like passengers on impossibly slow ships. The mantle learns its rhythm during these earliest eons, perfecting the art of heat transport that will drive plate tectonics for billions of years to come. The planet practices patience during these Hadean ages, cooling 1 degree at a time over millions of years, learning the fundamental rhythms that will govern 4 billion years of geological transformation. Time moves differently here, measured not in heartbeats or seasons, but in the slow breathing of an entire world, in the gradual transition from liquid to solid, from chaos to the first tentative order. The universe itself seems to hold its breath, waiting to see what this glowing ball of rock will become. Somewhere in this molten beginning, the story of continental drift begins not with movement, but with the promise of stillness, with the possibility that someday, somehow, this liquid world will cool enough to form solid ground that can wander. The first solid ground appears like islands of possibility rising from an ocean of liquid stone. These earliest patches of crust form not through any grand design, but through the simple physics of cooling. The outermost layer of the magma ocean finally drops below the melting point of basalt, creating a thin skin of solid rock floating on an interior that remains molten and restless. The crust breaks and reforms constantly, destroyed by the next asteroid impact or overwhelmed by fresh upwellings of lava, yet each time it returns, slightly thicker, slightly more persistent. These primordial continental fragments measure no larger than modern cities, perhaps the size of Manhattan or central London, tiny rafts of basalt drifting on a planetary sea of liquid rock. They form wherever the surface cools just enough to solidify, creating patches of dark, volcanic stone that glow cherry red at their edges where they meet the surrounding magma. The temperature difference between solid crust and molten interior creates its own weather patterns, convection cells that rise and fall like atmospheric storms, but made of rock instead of air, operating on time scales measured in millennia rather than days. Each fragment represents a small victory of order over chaos, of solid over liquid, though the victory remains temporary and fragile. Asteroid impacts still arrive with destructive regularity, instantly vaporizing any crust unlucky enough to lie beneath the point of collision. The largest impacts create craters hundreds of miles across, excavating so much material that they punch through the thin crust entirely, exposing the molten interior like wounds in the planet's skin. Only took a few million years for each crater to heal itself with fresh lava. The Earth notes with characteristic resilience. The chemistry of these first crustal patches differs subtly from anything that exists today. The early atmosphere contains almost no oxygen, creating reducing conditions that favor the formation of minerals rarely seen on the modern surface. Iron exists primarily in its metallic form, rather than as rust-red oxides, giving these ancient landscapes a dark, metallic sheen under the alien sky. Sulfur compounds dominate where volcanic gases meet the cooling rock, creating yellow and orange deposits that will disappear once oxygen-breathing life transforms the planet's chemistry. Scientists have discovered tiny zircon crystals in Australia that date back 4 billion years, microscopic time capsules that preserve chemical signatures from these earliest crustal fragments. The isotopic ratios locked within these crystals suggest that liquid water might have existed on Earth's surface much earlier than previously thought, perhaps pooling in low areas between the scattered patches of solid ground. This possibility remains one of geology's most tantalizing mysteries, whether the Hadean Earth experienced brief periods of surface cooling that allowed temporary oceans to form, only to be boiled away by the next major impact. The formation of solid crust creates the first possibility of topography elevation differences that will eventually become mountains and valleys. The earliest highlands rise where lighter minerals accumulate, floating on the denser underlying rock like foam on dark water. These proto-continents tower perhaps a few hundred feet above the surrounding magma, insignificant by modern mountain standards, but representing the first tentative steps toward the dramatic landscapes that will someday define Earth's surface. Beneath these floating fragments, the first hints of what will become mantle convection establish their deep patterns. Hot material rises from the planet's interior, spreads laterally beneath the crust, then sinks back down as it cools, creating circulation cells that operate like a planetary engine. These convection patterns determine where new crust forms and where existing fragments drift, establishing the fundamental mechanism that will eventually drive continental drift across billions of years. The mantle learns its choreography during these early eons, perfecting the slow dance that will someday carry entire continents around the globe. The surfaces of these early crustal fragments remain utterly barren, scoured clean by radiation from the young sun and subjected to temperature swings that would crack any complex molecules into their constituent atoms. No atmosphere thick enough to moderate climate exists, yet gases escape to space almost as quickly as volcanic outgassing produces them. The day-night temperature difference exceeds 1,000 degrees in some locations, causing thermal expansion and contraction that fractures the rock into angular blocks and rubble. Yet even in this hostile environment, the fundamental processes of weathering begin their patient work. Thermal cycling cracks the rock along crystal boundaries, while the first tentative chemical reactions alter mineral compositions at microscopic scales. These early weathering products remain trapped on the surface, unable to wash away in the absence of flowing water, accumulating as primitive regoliths that will someday become the raw material for sedimentary rocks. The gravitational influence of the nearby moon raises enormous tides in the magma ocean, creating bulges of molten rock that follow the lunar orbit around the planet. These tidal forces stress the thin crustal fragments, causing them to flex and crack with each 12-hour cycle. Some fragments split apart under this constant flexing, while others grow thicker and stronger, developing the structural integrity needed to survive the mechanical violence of the early Earth. Time passes with the patience characteristic of geological processes, each million-year interval bringing subtle changes that accumulate into transformation. The crustal fragments grow larger and more numerous, covering an increasing fraction of the planet's surface. The magma ocean gradually cools and thickens, becoming less fluid and more resistant to the tidal forces that once stirred it so easily. The bombardment from space continues but diminishes in intensity, allowing more fragments to survive long enough to merge with their neighbors. In this landscape of cooling stone and patient time, the first act of the continental drift story unfolds not as movement, but as the emergence of something solid enough to eventually move. These early crustal fragments float on their sea of liquid rock like the first tentative notes of a symphony that will play for billions of years, establishing the themes of creation, destruction, and reformation that will define Earth's geological future. The planet learns the art of making land, one cooling degree at a time. Water falls from ancient skies in the first rain Earth has ever known. The planet has cooled enough that water vapor can finally condense into droplets, gathering in clouds that cast shadows across the scattered patches of solid crust. These earliest rainstorms arrive with the violence of a world still learning weather, each drop striking the hot rock surface and instantly vaporizing back into steam, creating vast clouds that rise and fall in cycles lasting thousands of years. The water cycle begins its eternal dance, though in these early times it moves more like a cosmic percussion section than the gentle rhythm modern Earth will someday perfect. The atmospheric pressure remains far higher than anything a human could breathe, perhaps 10 or 20 times the density of modern air, thick with water vapor, carbon dioxide, and volcanic gases that would poison any oxygen-breathing life in minutes. Yet, this dense atmosphere serves as Earth's first blanket, trapping heat and moderating the extreme temperature swings that characterize the earliest crust formation. The greenhouse effect operates at maximum efficiency, keeping surface temperatures high enough that water exists primarily as vapor, waiting for the perfect moment to begin its transition to liquid. As the bombardment from space gradually diminishes, longer periods pass between major impacts, allowing the surface to cool in increments measured in hundreds of degrees rather than thousands. When surface temperatures finally drop below the boiling point of water at the prevailing atmospheric pressure, something unprecedented happens. Steam begins to condense, not just temporarily, but permanently, pooling in the lowest areas between the scattered continental fragments. The first oceans begin as puddles, then lakes, then shallow seas that reflect the alien light of a sun, younger and dimmer than the one that will someday warm human faces. These primordial oceans bear little resemblance to the blue waters that will later define Earth from space. The water runs dark and acidic, loaded with dissolved minerals leached from the volcanic crust and enriched with sulfur compounds that give it the chemistry of a planetary pickle brine. Iron dissolved in the water creates a greenish tint in some regions, while volcanic gases bubbling up from the seafloor add traces of hydrogen sulfide that would smell like rotten eggs to any creature capable of smelling. Only took a few 100 million years to fill the ocean basins. Time observes with its characteristic sense of geological humor. The process of ocean formation creates the first true interface between solid and liquid on Earth's surface, a boundary that will become one of the most dynamic and creative environments in the planet's history. Where water meets rock, chemical reactions begin that will eventually transform both the composition of the oceans and the minerals that make up the continents. The earliest weathering processes operate in this alien chemistry, breaking down volcanic rocks and carrying their dissolved components into the growing seas. These first oceans remain remarkably shallow compared to their modern descendants, rarely exceeding a few hundred feet in depth. The small size of the continental fragments means that most water collects in broad, shallow basins, rather than the deep abyssal plains that will characterize later ocean floors. Tidal ranges fluctuate wildly due to the moon's proximity, sometimes exposing vast areas of seafloor to the atmosphere, then flooding them again as the lunar orbit shifts. The boundary between land and sea shifts constantly, creating a constantly changing mosaic of wet and dry surfaces. The arrival of stable liquid water triggers the first truly global circulation patterns in Earth's climate system. Evaporation from the warm ocean surfaces feeds clouds that travel across the scattered continents, delivering rain that carves the first river channels and creates the earliest sedimentary deposits. These primitive rivers flow with water nearly as chemically aggressive as battery acid, dissolving minerals from the volcanic rocks and carrying them back to the sea in a circulation that will continue in various forms until the sun dies. Scientists remain uncertain about exactly when this transition to liquid oceans occurred, with estimates ranging from 4.4 billion to 3.8 billion years ago. The uncertainty arises partly from the complete absence of rocks from this period. Any surface rocks that might have recorded these events have long since been recycled by plate tectonics or destroyed by later bombardment. Researchers must reconstruct the story of Earth's first oceans from indirect evidence, the isotopic signatures of ancient zircon crystals, the chemistry of meteorites from this period, and computer models of early atmospheric evolution. The formation of oceans creates new possibilities for chemical concentration and transport that will prove crucial for the eventual origin of life. Dissolved minerals accumulate in enclosed basins where evaporation concentrates them into natural chemical laboratories. Hydrothermal vents begin operating on the seafloor, creating underwater geysers that inject hot, mineral-rich water into the primitive seas. These vents become oases of chemical complexity in an otherwise hostile world, mixing substances and creating conditions that will someday foster the first tentative experiments in self-replicating chemistry. The presence of liquid water also begins to lubricate the movement of the crustal fragments themselves. Water seeps into cracks and joints in the rock, weakening the bonds between mineral grains and making the crust more susceptible to tectonic forces. The earliest forms of what will eventually become plate tectonics begin to operate as water-weakened crustal blocks slide past each other with less resistance than the bone-dry rocks of the earliest Earth. Ocean currents establish their first circulation patterns, driven by temperature differences between the warm equatorial regions and cooler polar areas. These currents transport heat around the planet more efficiently than atmospheric circulation alone, beginning the process of global climate moderation that will make Earth uniquely suitable for complex life. The oceans become the planet's first circulatory system, moving not just water but dissolved chemicals, heat, and eventually nutrients around the globe with the patient persistence that characterizes all oceanic circulation. In the growing darkness of evening on this ancient world, the first waves lap against shores of black volcanic rock, creating sounds that no ear has yet evolved to hear. The rhythm of wave against stone begins its 4 billion-year percussion, gradually wearing down the sharpest edges of the continents and beginning the process of coastal erosion that will shape every shoreline Earth will ever know. Water has found its home on the planet's surface, and in finding that home, it creates the conditions that will make all future homes possible. Stone rafts begin to wander across Earth's surface with the patience of deep time, carried by forces hidden beneath the planet's newly formed crust. These earliest continental fragments, no larger than modern islands, drift across the shallow seas on currents of molten rock that flow with the viscosity of cold honey. The movement occurs so slowly that a human observer would perceive only stillness. Yet across millions of years, these patches of solid land trace complex paths across the globe like leaves floating on a vast, invisible river. The mechanism driving this movement lies deep in the planet's interior, where radioactive decay generates heat faster than the young Earth can radiate it away into space. Uranium, thorium, and potassium atoms split apart in the mantle, releasing energy that has nowhere to go but upward, creating convection cells that rise from the core mantle boundary like thermal elevators operating on geological timescales. These rising plumes of hot rock push against the underside of the crust, creating pressures that crack and separate the continental fragments, setting them adrift on their first tentative journeys. The early mantle contains far more radioactive elements than it will in later eons, making it a more vigorous heat engine than the one that drives modern plate tectonics. This enhanced radioactivity creates a more chaotic convection pattern, with hotspots appearing and disappearing unpredictably across the planet's interior. The continental fragments respond to these changing thermal currents like ships on a stormy sea, sometimes clustering together in temporary archipelagos, sometimes dispersing across vast distances of open ocean. Each fragment carries within its rocks a magnetic signature that records the orientation of Earth's magnetic field at the time of its formation. These paleomagnetic clues, locked in iron-bearing minerals as they cool below the Curie temperature, serve as compasses pointing toward ancient magnetic poles. Scientists studying much later rocks can read these magnetic memories like a ship's log, reconstructing the wandering paths of continents across billions of years. Only took the planet 4 billion years to learn celestial navigation. The geological record notes with dry satisfaction. The collisions between wandering fragments occur with spectacular slowness, unfolding over millions of years as inexorable pressure builds along the boundaries where moving crusts meet. When two pieces of early continent finally touch, the impact releases energy gradually, like a handshake that lasts for millennia. The edges of the colliding fragments crumple and fold, creating the first mountain ranges as rock layers buckle upward under compression that would crush any material less patient than stone. These earliest mountains rise grain by grain, each crystal of quartz and feldspar climbing toward the sky at rates measured in millimeters per century. The mountains grow through a combination of folding, where rock layers bend like pages in a closing book, and thrust faulting, where entire sheets of crust slide over their neighbors in movements so gradual they seem frozen in time. Erosion begins immediately, racing against mountain building in a contest that will continue for the remainder of Earth's history. The wandering fragments leave behind them trails of geological evidence that speak of their journeys across the early Earth. Volcanic chains mark the paths of crustal blocks as they pass over stationary hotspots in the mantle, creating linear arrangements of extinct volcanoes like breadcrumbs marking a route through the geological wilderness. The chemistry of these ancient volcanic rocks varies with latitude, recording changes in the composition of the upper mantle as the fragments drift from equatorial to polar regions. Between the wandering continents, new ocean floor forms to fill the gaps left by separation. This oceanic crust differs fundamentally from the continental fragments, denser, thinner, and dominated by dark basaltic rocks rather than the lighter granites that will eventually characterize true continents. The new seafloor spreads outward from volcanic ridges like a conveyor belt made of stone, creating symmetric patterns of magnetic stripes as Earth's magnetic field reverses polarity at irregular intervals. The early oceans serve as more than just passive spaces between moving continents. They actively participate in the drift process through their influence on crustal temperatures and chemical weathering. Seawater penetrates deep into fractured rocks along the edges of the fragments, carrying heat away from the interior and lubricating the boundaries where movement occurs. The chemical interaction between seawater and hot volcanic rock creates new minerals that are softer and more plastic than their dry counterparts, facilitating the sliding motion that allows continents to move. Scientists remain puzzled by some aspects of this early continental drift, particularly the question of whether true plate tectonics operated during the Hadean and Archean eons, or whether the movement of crustal fragments followed different rules than those governing modern continental drift. The higher radioactivity and temperature of the early mantle may have created a more chaotic system, with smaller, more numerous plates moving in less predictable patterns than the well-organized dance of modern tectonics. The atmosphere above these wandering continents remains alien by modern standards, thick with water vapor and volcanic gases, but entirely devoid of free oxygen. This reducing atmosphere creates unique weathering conditions that preferentially dissolve certain minerals while preserving others, influencing both the composition of the wandering fragments and the chemistry of the seawater through which they move. The lack of oxygen means that iron remains in its metallic form, creating landscapes with a silvery gray appearance under the perpetually cloudy skies. Temperature gradients between the equatorial and polar regions drive atmospheric circulation patterns that influence the movement of the continental fragments through their effect on ocean currents and heat distribution. The wandering pieces of crust encounter different climate conditions as they drift between latitudes, experiencing tropical heat near the equator and cooler temperatures toward the poles. These climate variations create thermal stresses that contribute to the fracturing and separation of crustal blocks. As millions of years accumulate into tens of millions, then hundreds of millions, the pattern of continental drift becomes more organized and predictable. The mantle convection system matures, developing the more stable circulation patterns that will eventually create the large-scale plate motions characteristic of modern Earth. The wandering fragments begin to respond to these deeper currents, like iron filings aligning with a magnetic field. Their random wandering gradually giving way to the systematic movements that will dominate the next 4 billion years of Earth's history. In the patient darkness of geological time, the stone rafts continue their wandering across the shallow seas, carrying within their crystalline memories the record of a planet learning to move. Each fragment serves as both passenger and navigator on currents that flow through solid rock, writing the first chapters of a story that will continue until the sun expands and boils away the oceans that make their movement possible. The dance of colliding lands begins with a tenderness that belies the immense forces at work beneath the Earth's surface. Two continental fragments approach each other across the dark ocean at the speed of growing fingernails. Their collision inevitable, yet so gradual that entire mountain ranges have time to rise and erode between the moment contact begins and the final joining is complete. The impact unfolds over tens of millions of years, each millennium bringing the opposing shores incrementally closer until the shallow seas between them disappear entirely, replaced by zones of crumpled rock that record the patient violence of crustal compression. The first contact occurs not between the continental fragments themselves, but between the thin oceanic crust that separates them. As the distance narrows, this intervening seafloor begins to buckle and fold, creating underwater mountain ranges that rise from the abyssal depths like slow-motion tsunamis made of stone. The oceanic crust, denser than the continental material it separates, eventually surrenders to gravity and slides beneath one of the approaching landmasses in the process that will later be called subduction. Though these early examples operate according to rules slightly different from their modern descendants, the subducting oceanic crust carries with it vast quantities of seawater, which penetrate deep into the Earth's interior and trigger volcanic activity along the edge of the overriding continent. These volcanic arcs create chains of mountains that parallel the collision zone, building upward grain by grain as magma generated by the melting oceanic crust finds its way to the surface. The volcanoes erupt with the regularity of a geological heartbeat, each eruption adding layers of ash and lava to the growing mountain chain while simultaneously poisoning the atmosphere with sulfur compounds and particulates that dim the sun for years at a time. When the continental fragments themselves finally make contact, the collision creates something unprecedented in Earth's short history: genuine mountain ranges that tower thousands of feet above the surrounding landscape. The edges of the colliding continents compress like crumpled paper, but paper that requires millions of years to fold and unfold. Rock layers that once lay horizontal beneath ancient seas now stand vertical or even overturned, creating geological formations that seem to defy gravity until one considers the immense pressures required to bend solid stone into such impossible configurations. The mountains rise through a combination of folding and faulting that operates simultaneously on multiple scales. Individual mineral grains recrystallize under pressure, growing larger and more perfectly formed as they adjust to their new high-pressure environment. Rock layers slide over each other along fault planes that extend deep into the crust, carrying pieces of ancient seafloor to elevations where they will someday puzzle geologists trying to understand how marine fossils came to rest on mountain peaks. Only took 100 million years to turn a seabed into a summit. Time notes with characteristic patience. Between the rising peaks, valleys form that channel the first significant rivers Earth has known. These early waterways flow with unprecedented volume as the new mountains wring moisture from passing clouds, creating precipitation patterns that concentrate rainfall on the windward slopes while leaving rain shadows in the lee. The rivers carry enormous loads of sediment eroded from the rapidly rising peaks, depositing this material in growing deltas and coastal plains that expand the continental margins outward into the surrounding seas. The collision process generates more than just mountains. It creates the first truly thick continental crust, fundamentally different from the thin oceanic crust that covers most of the planet's surface. This continental crust consists of lighter minerals that resist subduction, creating permanent additions to the landmasses that will persist through billions of years of subsequent geological activity. The collision zones become nurseries for new continental material, alchemical laboratories where oceanic crust transforms into the granitic rocks that will eventually form the cores of all future continents. Deep beneath the collision zone, temperatures and pressures reach levels that fundamentally alter the mineral composition of the crustal rocks. Limestone transforms into marble, sandstone becomes quartzite, and shale recrystallizes into slate and schist in a process called metamorphism that creates entirely new categories of rock. These metamorphic minerals provide a detailed record of the conditions that prevailed during mountain building, their crystal structures encoding information about pressure, temperature, and chemical environment that allows scientists to reconstruct the collision process millions of years after it concluded. The collision affects more than just the rocks directly involved in the impact. It creates shock waves that propagate through the solid Earth, triggering earthquakes and volcanic activity thousands of miles from the collision zone itself. These distant effects create a network of geological connections that link events across entire hemispheres, establishing the principle that no part of the Earth exists in isolation from any other part. The planet begins to function as an integrated system, where forces applied in one location generate responses across the entire globe. Scientists studying these ancient collision zones face the challenge of reading geological stories written in a language that Earth was still learning to speak. The rock record from this period remains fragmentary and often contradictory, with different lines of evidence suggesting different interpretations of the same events. Some collision zones seem to have operated according to modern plate tectonic principles, while others appear to follow rules that make little sense in the context of present-day continental drift. The atmospheric consequences of these early mountain-building episodes extend far beyond the immediate collision zones. The newly exposed rock surfaces weather rapidly in the warm, humid climate, consuming carbon dioxide from the atmosphere through chemical reactions that will eventually help stabilize Earth's climate system. The mountains also alter atmospheric circulation patterns, creating new weather systems and precipitation regimes that influence climate across entire continents. As each collision concludes and the mountain-building forces relax, erosion begins its patient work of wearing down the newly created peaks. Rivers cut deeper valleys. Glaciers that form on the highest summits carve characteristic U-shaped valleys, and chemical weathering gradually dissolves the more soluble minerals, leaving behind the resistant cores that will form the ancient shields found at the heart of every modern continent. The mountains that required tens of millions of years to build are surrendered to erosion over similar timescales, their substance redistributed across the growing continental margins as sedimentary deposits that will someday become new mountains in future collision cycles. The dance of colliding lands establishes the fundamental rhythm of continental growth and recycling that will characterize the remainder of Earth's geological history. Each collision creates new continental crust while simultaneously destroying oceanic crust, gradually increasing the total area of land surface while maintaining the overall balance between creation and destruction that keeps the planet's surface in dynamic equilibrium. The continents learn to grow through collision, establishing a pattern of episodic mountain building that will continue until the planet's internal heat engine finally runs down billions of years in the future. Beneath the crust, rivers of rock flow with currents that dwarf any movement the surface world will ever know. These streams of molten stone rise from depths where pressure transforms solid matter into something between liquid and gas, creating convection cells that span thousands of miles and operate for hundreds of millions of years with the persistence of planetary breathing. The mantle moves in patterns so vast and slow that they exist beyond human comprehension. Yet these invisible currents drive every earthquake, every volcanic eruption, every mountain range that will ever grace the Earth's surface. The heat that powers these deep currents comes primarily from radioactive decay occurring throughout the planet's interior, where uranium and thorium atoms split apart with clockwork precision, each decay event releasing a tiny burst of energy that accumulates into the thermal engine that will drive continental drift for billions of years. The early Earth contains far more of these radioactive elements than it will in later eons, making the young planet's interior significantly hotter and more vigorous than the cooler, more sedate system that will characterize the modern world. This enhanced radioactivity creates a more chaotic convection pattern, with rising plumes of hot rock appearing and disappearing unpredictably across the core mantle boundary like thermal tornadoes made of molten stone. The convection cells organize themselves into patterns that persist for geological ages, each cell spanning thousands of miles in diameter and reaching from near the core to just beneath the crust. Hot material rises at the center of each cell, spreads laterally beneath the surface, then cools and sinks back down at the cell's edges in a circulation pattern that operates like a planetary furnace. These rising currents create hotspots that burn through the overlying crust like cosmic blowtorches, generating volcanic activity that continues for millions of years as the crustal plates drift slowly across the stationary mantle plumes. The boundaries between convection cells become zones of particular geological significance, creating linear features on the surface that mark where rising currents diverge or where sinking currents converge. These boundaries shift and migrate over geological time as the convection pattern reorganizes itself in response to changes in the planet's internal heat production and distribution. Only took 3 billion years for the mantle to learn efficient circulation. The deep Earth observes with the patience characteristic of planetary scale phenomena. The speed of mantle convection remains almost incomprehensibly slow by surface standards, with velocities measured in centimeters per year rather than the meters per second typical of fluid flow in more familiar contexts. Yet this seemingly glacial pace represents rapid motion when considered in the context of solid rock flow, requiring temperatures and pressures so extreme that the normal rules of material behavior cease to apply. The rock flows like thick honey, deforming continuously under stress while maintaining enough structural integrity to transmit forces across thousands of miles. Between the rising and falling limbs of each convection cell, horizontal currents transport heat and material across vast distances beneath the surface. These lateral flows create drag forces that pull the overlying crustal plates along like leaves floating on a slow-moving stream, providing the primary driving mechanism for continental drift. The coupling between mantle flow and crustal movement operates through friction and thermal expansion, with the hot, rising currents pushing upward against the plate boundaries, while the cool, sinking currents pull downward on the edges of the plates. The three-dimensional structure of mantle convection creates a complex network of thermal currents that interact with each other in ways that remain partially mysterious even to modern geophysicists. Computer models suggest that the convection pattern may include multiple layers operating at different scales, with small, fast-moving cells near the surface interacting with larger, slower-moving cells that extend deep into the lower mantle. These multi-scale interactions create a rich variety of surface phenomena, from the linear volcanic chains that mark hotspot tracks to the complex patterns of mountain building that occur where plates collide. The chemistry of the mantle varies subtly from region to region, creating convection currents with different compositions that produce distinctly different types of volcanic activity when they reach the surface. Some plumes carry material rich in iron and magnesium, generating the dark, dense basalts that form oceanic crust, while others transport lighter, more silica-rich material that creates the granitic rocks characteristic of continental crust. This chemical heterogeneity develops over billions of years as subducted oceanic crust mixes with pristine mantle material, creating a complex mosaic of compositions that influences the long-term evolution of the planet's surface. The temperature contrast between the hot core and the cool surface creates the primary driving force for mantle convection, but the pattern of circulation also depends on the planet's rotation, which generates Coriolis forces that deflect rising and sinking currents into spiral patterns. These rotational effects become more pronounced as the convection cells grow larger, creating characteristic signatures in the magnetic field patterns recorded in volcanic rocks that provide clues about the ancient structure of mantle flow. Scientists studying modern mantle convection face the challenge of inferring three-dimensional flow patterns from two-dimensional surface observations, like trying to understand ocean currents by watching only the waves that reach the shore. Seismic waves generated by earthquakes provide the primary tool for mapping the internal structure of convection cells, revealing the locations of hot and cold regions through their effects on wave propagation speed. These seismic tomography studies have revealed a complex internal structure that includes both broad, sheet-like upwellings and narrow, pipe-like plumes that rise from the deepest parts of the mantle. The interaction between mantle convection and the overlying crust creates feedback mechanisms that influence the long-term evolution of both systems. The formation of thick continental crust acts as an insulating blanket that traps heat in the underlying mantle, potentially altering local convection patterns and creating new zones of upwelling or downwelling. Similarly, the subduction of cold oceanic crust introduces thermal anomalies into the mantle that can persist for hundreds of millions of years, influencing convection patterns across entire geological eras. As the planet ages and its internal heat production gradually decreases through radioactive decay, the vigor of mantle convection slowly diminishes, leading to larger, more stable convection cells and less chaotic surface tectonics. This thermal evolution represents a fundamental constraint on the long-term habitability of the planet, as the eventual cessation of mantle convection will shut down the plate tectonic system that regulates Earth's climate and maintains the chemical cycles necessary for life. Deep beneath the wandering continents and the growing mountain ranges, the rivers of rock continue their patient circulation, carrying heat from the planet's interior to its surface with the persistence of geological time itself. These currents, invisible to any observer on the surface, represent the true circulatory system of the planet, the underground rivers that make all surface rivers possible, the hidden heartbeat that drives the pulse of continental drift across the vast expanse of deep time. The birth of supercontinents begins not as a single dramatic event, but as the gradual convergence of wandering fragments across hundreds of millions of years, each collision adding mass and complexity to growing landmasses that will eventually dwarf the scattered islands from which they arose. The continental fragments, driven by the deep currents of mantle convection, follow invisible paths that slowly spiral inward toward points of convergence, like cosmic debris gathering into planetary whirlpools made of stone and time. The first supercontinent assembles itself through this patient process of accretion, growing larger and more coherent with each addition until it encompasses nearly all of Earth's continental crust in a single, vast landmass surrounded by an equally vast ocean. This early supercontinent, which scientists call Valbara or depending on which fragments they consider most significant, represents a fundamentally different kind of landmass than anything that exists on the modern Earth. Unlike later supercontinents that form through the collision of pre-existing continents, this first great landmass grows primarily through the addition of small, crustal fragments and volcanic arcs, building itself piece by piece like a geological jigsaw puzzle whose final image remains unknown until the last piece falls into place. The assembly process operates through the same tectonic mechanisms that create individual mountain ranges, but scaled up to continental proportions and extended across geological ages. The forces driving supercontinent assembly arise from the large-scale organization of mantle convection into patterns that favor convergence rather than dispersion. As the Earth's internal heat production stabilizes and the chaotic convection patterns of the earliest eons give way to more organized circulation, the mantle develops large-scale flows that sweep crustal fragments toward preferred zones of convergence. These convergence zones become the assembly points for supercontinents, locations where multiple plates meet and merge over periods measured in hundreds of millions of years. The growing supercontinent fundamentally alters the planet's surface geography, creating for the first time a clear distinction between a massive continental interior and an equally massive oceanic exterior. This continental interior experiences climate conditions unlike anything that existed when the land masses remained small and scattered, with vast areas located thousands of miles from the moderating influence of the ocean. The interior regions develop extreme continental climates, with scorching summers and frigid winters that create temperature ranges far exceeding anything possible on smaller landmasses surrounded by water. The assembly of the supercontinent also creates the first truly deep ocean basins, as the oceanic crust between converging continents gets consumed by subduction, allowing the remaining ocean floor to subside to depths approaching those found in modern oceans. These deep basins develop their own circulation patterns that differ dramatically from the shallow, continent-dotted seas that characterized earlier periods, creating new opportunities for chemical concentration and thermal stratification that will influence ocean chemistry for hundreds of millions of years. Only took 500 million years to dig a proper ocean. The planet notes with satisfaction at this milestone in surface organization. The supercontinent's massive size creates its own gravitational anomalies that influence the planet's rotation and the distribution of mass within the Earth system. The concentration of so much continental crust in one hemisphere creates an imbalance that affects the planet's moment of inertia, potentially influencing the length of the day and the stability of the rotational axis. These effects remain subtle by human standards, but become significant when integrated over geological timescales, contributing to long-term changes in climate and ocean circulation patterns. Mountain building within the supercontinent operates on scales impossible when continental fragments remained isolated from each other. The collision zones between major crustal blocks create mountain ranges that extend for thousands of miles across the continental interior, forming linear belts of high topography that channel atmospheric circulation and create rain shadows affecting areas the size of modern continents. These mountain belts serve as the supercontinent's backbone, providing structural integrity that helps hold the massive landmass together against the tectonic forces that will eventually tear it apart. The volcanic activity associated with supercontinent assembly operates through multiple mechanisms that create different types of igneous rocks in different tectonic settings. Subduction zones around the supercontinent's perimeter generate explosive volcanic arcs that build island chains and coastal mountain ranges, while collision zones in the interior create conditions for the formation of granitic plutons that will become the crystalline cores of future continents. Hotspots burning through the thick continental crust generate flood basalts that cover vast areas with layers of volcanic rock hundreds of feet thick. The weathering of the supercontinent's massive land surface creates sedimentary processes operating on scales unprecedented in Earth's earlier history. Rivers draining the continental interior carry enormous loads of sediment thousands of miles to the sea, creating delta systems and continental margins that extend hundreds of miles offshore. The chemical weathering of so much exposed continental crust consumes atmospheric carbon dioxide at accelerated rates, potentially influencing global climate through the greenhouse effect and creating feedback mechanisms between continental assembly and atmospheric composition. Scientists studying these ancient supercontinents face the challenge of reconstructing continental configurations from rocks that have been subjected to billions of years of subsequent tectonic activity, erosion, and metamorphism. The evidence for early supercontinent assembly comes primarily from the matching of geological features across modern continental boundaries, the analysis of paleomagnetic data that records ancient latitudes and orientations, and the correlation of isotopic signatures that reveal common origins for rocks now separated by thousands of miles of ocean. The lifespan of the first supercontinent remains uncertain, with estimates ranging from a few 100 million years to more than 1 billion years of stability before the forces that assembled it reverse direction and begin the process of continental breakup. The same mantle convection patterns that drove convergence and assembly eventually reorganize themselves into patterns that favor divergence and dispersal, setting the stage for the cyclic assembly and breakup of supercontinents that will characterize the remainder of Earth's geological history. The supercontinent creates new environments for the concentration and preservation of mineral resources, as the vast continental interior provides stable platforms where sedimentary and volcanic processes can operate without interruption for hundreds of millions of years. These stable continental interiors become the depositories for many of the mineral resources that will later be essential for the development of complex life and, eventually, human civilization. Creating ore deposits through processes that require both the vast scale and long-term stability that only supercontinents can provide. As the supercontinent reaches its maximum extent, it represents a unique moment in Earth's history when nearly all continental crust exists as part of a single, integrated landmass. This configuration creates opportunities for the exchange of materials and organisms across vast distances by land routes, while simultaneously creating barriers to oceanic circulation that will influence climate patterns for hundreds of millions of years. The supercontinent stands as Earth's first experiment in continental organization, a prototype for the larger and more complex supercontinents that will follow in later geological eras. In the patient darkness of deep time, the supercontinent grows grain by grain, collision by collision, until it spans a significant fraction of the planet's surface, demonstrating for the first time the Earth's capacity to organize its scattered fragments into coherent wholes before scattering them again in the eternal dance of assembly and dispersal that defines the rhythm of geological time. When Pangaea held the world, the planet wore a single, massive scar of land that stretched from pole to pole across one hemisphere, while the rest of Earth lay hidden beneath Panthalassa, an ocean so vast it contained more water than all modern seas combined. This most recent supercontinent represents the culmination of hundreds of millions of years of continental assembly, the final gathering of crustal fragments that had wandered separately since the breakup of earlier supercontinents. Pangaea achieves a completeness that earlier attempts at continental unification never quite managed, collecting virtually every piece of continental crust into a single landmass, roughly shaped like a giant comma punctuating the planet's surface with unprecedented geological grammar. The supercontinent spans nearly 180 degrees of longitude at its widest point, creating continental interiors located more than 2,000 miles from the nearest ocean. These inland regions experience climatic extremes unknown on the modern Earth, where no location lies more than a few hundred miles from oceanic moderation. Summer temperatures in Pangaea's interior soar above 120 degrees Fahrenheit across areas larger than modern Asia, while winter cold penetrates deep into the continental mass, creating seasonal temperature swings that approach 100 degrees across vast portions of the landmass. The monsoon systems that develop to transport moisture from the distant oceans into the continental interior operate on scales that dwarf any modern weather patterns. The assembly of Pangaea creates mountain ranges that exceed anything built during previous episodes of continental collision, partly because the converging landmasses themselves are larger and more massive than the fragments that created earlier supercontinents. The Appalachian Ouachita Marathon mountain system extends for thousands of miles across the eastern margin of the supercontinent, while the Urals mark the suture where the Siberian continent welded itself to the rest of Pangaea. These mountain belts rise to elevations approaching those of the modern Himalayas, creating topographic barriers that influence atmospheric circulation across the entire supercontinent. The ocean that surrounds Pangaea develops circulation patterns unlike anything seen before or since in Earth's history. Panthalassa covers nearly 3/4 of the planet's surface, creating oceanic gyres thousands of miles in diameter that transport heat and nutrients across distances spanning entire hemispheres. The Tethys Sea, a large embayment that penetrates deep into Pangaea's eastern margin, becomes a crucial pathway for oceanic circulation and a laboratory for the evolution of marine life in semi-enclosed conditions, only took 250 million years to build the ultimate supercontinent. Geological time observes with the satisfaction that comes from achieving maximum continental organization. The formation of Pangaea profoundly influences global climate patterns through its effects on oceanic and atmospheric circulation. The concentration of so much landmass in one hemisphere disrupts the normal pattern of heat transport from equatorial to polar regions, creating climate instabilities that contribute to some of the most dramatic environmental changes in Earth's history. The end Permian mass extinction, the most severe biological crisis ever recorded, coincides with Pangaea's peak assembly and may result partly from the climatic disruptions caused by the supercontinent's massive size and unusual geography. Volcanic activity associated with Pangaea's final assembly operates through multiple mechanisms that create some of the largest igneous provinces in Earth's history. The Siberian Traps, covering an area larger than Western Europe with layers of basalt up to several miles thick, form as a massive hotspot burns through the newly assembled supercontinent. This volcanic episode releases enormous quantities of carbon dioxide and sulfur compounds into the atmosphere, creating greenhouse conditions that raise global temperatures by more than 10 degrees Celsius and acidify the oceans to levels approaching those of battery acid. The interior of Pangaea becomes a vast laboratory for terrestrial evolution as life forms adapt to the extreme continental climates and the absence of oceanic barriers that previously separated different biogeographic provinces. The supercontinent creates the first truly global terrestrial ecosystem, allowing the exchange of organisms across distances that span thousands of miles and multiple climate zones. This biological mixing leads to both increased competition and increased opportunities for evolutionary innovation as species encounter new environments and ecological challenges. The geological processes operating within Pangaea create some of the most economically important mineral deposits in Earth's history, as the stable continental interior provides platforms for the concentration of resources through sedimentary and hydrothermal processes. The vast desert systems that develop in the supercontinent's interior create conditions for the formation of evaporite deposits and red beds that will later become important sources of salt, potash, and other industrial minerals. The collision zones that mark the boundaries between the constituent continents generate ore deposits through metamorphism and igneous intrusion on scales commensurate with the massive size of the converging landmasses. The breakup of Pangaea begins while the supercontinent is still growing, as the same mantle convection patterns that drove its assembly start to reorganize themselves into configurations that favor divergence rather than convergence. The first rifts appear in the continental interior as rising mantle plumes create zones of thermal doming that stretch and thin the overlying crust. These early rifts develop into the failed arms of three-way junction systems, with one arm eventually becoming the site of successful continental separation, while the other two arms remain as fossil rift valleys preserved within the separating continents. Scientists studying Pangaea possess more complete geological evidence for its structure and evolution than for any earlier supercontinent, partly because the rocks formed during its assembly and breakup are young enough to have survived subsequent geological processes with less alteration than older rocks. The magnetic stripes preserved in the oceanic crust formed during Pangaea's breakup provide detailed records of the separation process, while the matching geological features across modern continental margins allow precise reconstruction of the supercontinent's original configuration. The duration of Pangaea's existence as a fully assembled supercontinent spans approximately 100 million years, from its final assembly around 300 million years ago to the beginning of significant breakup around 200 million years ago. This lifespan proves typical for supercontinents, which seem to follow a predictable cycle of assembly, stability, and dispersal driven by the evolving patterns of mantle convection beneath them. The cycle operates on timescales of 400 to 600 million years, suggesting that Pangaea represents just one phase in a process that has repeated multiple times throughout Earth's history. The legacy of Pangaea persists in the modern world through the distribution of continents, ocean basins, and mountain ranges that result from its breakup. The Atlantic Ocean opens as a direct consequence of Pangaea's separation, while the modern positions of the continents reflect their original locations within the supercontinent modified by 200 million years of subsequent drift. The biological distributions that developed during Pangaea's existence continue to influence modern biogeography, with related species found on continents, now separated by thousands of miles of ocean, serving as living testimony to their former connection within the supercontinent. In the vast context of geological time, Pangaea represents both an ending and a beginning, the culmination of one cycle of continental assembly and the starting point for another cycle of dispersal and eventual reassembly that will continue until the Earth's internal heat engine finally runs down billions of years in the future. The supercontinent stands as Earth's most recent experiment in maximum continental organization, a temporary arrangement of crustal fragments that demonstrates both the planet's capacity for large-scale organization and its inevitable tendency toward change and rearrangement across the patient expanse of deep time. The Great Rift opens with the patience of geological time, beginning not as a dramatic fracture, but as a subtle doming of the land surface above rising currents of hot mantle rock. Pangaea stretches like skin pulled tight across expanding bones, the continental crust thinning and weakening along zones where thermal plumes burn upward from the deep earth with temperatures exceeding those found in steel foundries. These thermal anomalies create broad uplifts hundreds of miles across, raising the land surface by thousands of feet and generating gravitational stresses that eventually overcome the tensile strength of solid rock. The supercontinent begins to pull itself apart along these zones of weakness, initiating the process that will eventually scatter its fragments across the globe once again. The first visible signs of continental breakup appear as linear valleys that cut across the landscape like surgical incisions made by planetary forces operating on scales beyond human comprehension. These rift valleys form where the continental crust stretches and thins, creating grabens bounded by normal faults that drop the Central Valley floor relative to the surrounding highlands. The East African rift system provides a modern example of this process in its early stages, showing how continental breakup begins with the formation of elongated depressions that gradually widen and deepen over millions of years until they eventually reach sea level and allow oceanic crust to form between the separating continental margins. The rifting process operates through a combination of active and passive mechanisms that work together to weaken and eventually sever the continental lithosphere. Active rifting occurs where rising mantle plumes push upward against the base of the continental crust, creating thermal domes that stretch the overlying rocks beyond their elastic limit. Passive rifting results from far-field tectonic stresses that pull the continents apart, with the lithosphere responding to these extensional forces by developing zones of weakness that eventually become sites of continental separation. The relative importance of these mechanisms varies from one rift system to another, creating different styles of continental breakup that leave distinctive geological signatures. Volcanic activity accompanies the rifting process, as decompression melting in the rising mantle generates magmas that find their way to the surface through the fractured and thinned continental crust. These rift-related volcanoes differ from those associated with subduction zones or hotspots, producing distinctive suites of alkaline lavas that reflect the unique chemical conditions created by continental extension and mantle upwelling. The volcanic rocks provide important constraints on the timing and mechanism of continental breakup, preserving within their crystalline structure records of the temperatures, pressures, and chemical conditions that prevailed during the early stages of rifting. The sedimentary rocks that accumulate in the developing rift valleys record the environmental changes that accompany continental breakup, preserving evidence of the climatic and topographic evolution that occurs as the rift system deepens and widens. Early rift sediments consist primarily of alluvial fan deposits and playa lake sediments that accumulate in closed basins with no outlet to the sea, while later sediments include evaporates and marine carbonates that indicate the eventual connection between the rift valley and the global ocean system. Only took 50 million years to turn a highland into a seaway. The patient earth notes with characteristic understatement, the transition from continental rifting to oceanic spreading marks a fundamental change in the character of the breakup process, as the formation of new oceanic crust between the separating continental margins creates a self-sustaining mechanism for continued separation. The first oceanic crust forms when the continental lithosphere becomes so thin and hot that decompression melting produces basaltic magmas that erupt onto the rift valley floor, creating the distinctive pillow lavas and sheeted dike complexes that characterize oceanic crust formation. This transition typically occurs when the total amount of extension reaches 100 to 200% of the original continental width, though the exact threshold varies depending on the thermal structure and composition of the extending lithosphere. The newly formed oceanic crust spreads away from the rift axis at rates measured in centimeters per year, creating symmetric patterns of magnetic stripes that record the history of geomagnetic field reversals during the spreading process. These magnetic anomalies provide one of the most precise tools available for reconstructing the timing and kinematics of continental breakup, allowing scientists to trace the positions of the separating continents back through time with remarkable accuracy. The magnetic stripes also reveal variations in spreading rate that reflect changes in the driving forces responsible for continental separation. The breakup of Pangaea does not occur simultaneously across the entire supercontinent, but proceeds through a complex sequence of rifting events that affect different parts of the landmass at different times. The earliest rifts develop in the Triassic period, along what will eventually become the eastern margin of North America, while the opening of the South Atlantic does not begin until the Jurassic period, and the separation of Antarctica from Australia continues well into the Cenozoic era. This diachronous breakup reflects the complex three-dimensional structure of mantle convection beneath the supercontinent, with different regions responding to different thermal and mechanical forcing mechanisms. The chemical and isotopic evolution of the mantle beneath the rifting supercontinent creates distinctive signatures in the volcanic rocks produced during continental breakup, allowing geochemists to trace the sources of the magmas and the processes responsible for their generation. Some rift-related volcanic rocks show evidence for melting of ancient lithospheric mantle that was modified by previous episodes of subduction, while others reflect the involvement of relatively pristine mantle material rising from greater depths. This chemical diversity provides insights into the complex three-dimensional structure of the mantle and the processes responsible for continental breakup. The atmospheric and oceanic consequences of Pangaea's breakup extend far beyond the immediate effects of rifting and volcanism, influencing global climate patterns through changes in oceanic circulation and heat transport. The opening of new ocean basins creates opportunities for the development of new oceanic gyres and current systems, while the separation of continental landmasses eliminates barriers to atmospheric circulation that existed during the supercontinent phase. These changes in ocean and atmosphere circulation patterns contribute to long-term climate evolution and may help explain some of the major environmental changes that occur during the Mesozoic era. The biological consequences of continental breakup prove equally profound, as the separation of previously connected landmasses creates new opportunities for allopatric spaciation, while simultaneously eliminating migration routes that allowed genetic exchange between populations. The breakup of Pangaea sets the stage for the independent evolution of terrestrial biotas on different continents, leading to the distinctive biogeographic patterns that characterize the modern world. The timing of continental separation relative to major evolutionary innovations influences which groups of organisms achieve global distributions and which remain restricted to particular continental fragments. The Great Rift widens year by year, millennium by millennium, creating new ocean floor between the separating continental margins while simultaneously destroying oceanic crust elsewhere through subduction, maintaining the overall balance between creation and destruction that keeps the Earth's surface area constant. The breakup of Pangaea represents neither an end nor a beginning, but rather one phase in the endless cycle of supercontinent assembly and dispersal that has characterized Earth's evolution for billions of years, driven by the patient circulation of the mantle that will continue until the planet's internal heat engine finally runs down in the distant future. Atlantic Ocean learns to breathe with the slow rhythm of seafloor spreading, inhaling new basaltic crust at the mid-Atlantic ridge while exhaling ancient oceanic lithosphere into subduction zones thousands of miles away. The infant ocean begins as a narrow seaway no wider than the modern Red Sea, its shores lined with the fractured edges of North America, Europe, Africa, and South America as they drift apart with the measured pace of growing fingernails. Each year brings these continental margins a few centimeters farther from each other, a separation so gradual that entire mountain ranges rise and erode in the time required for the ocean to double its width. The spreading ridge that bisects the Atlantic operates like a vast underwater conveyor belt, manufacturing new ocean floor through volcanic processes that occur in perpetual darkness beneath miles of seawater. Magma rises from the mantle through a narrow zone of crustal weakness, erupting as pillow lavas that cool instantly in contact with the frigid deep water, creating the characteristic bulbous forms that mark oceanic volcanism. The newly formed basaltic crust spreads away from the ridge axis at rates averaging 2 to 3 centimeters per year, slow enough that the volcanic activity proceeds without dramatic upheavals, yet fast enough to create an entire ocean basin over the span of geological time. The magnetic signatures locked into the cooling basalt as it forms create a zebra stripe pattern of normal and reversed polarity zones that extend symmetrically away from the spreading ridge like pages in an open book recording Earth's magnetic field history. Each stripe represents a period when the planet's magnetic field pointed either north or south, with the transitions between normal and reversed polarity occurring at irregular intervals averaging several 100,000 years. These magnetic anomalies provide one of the most precise chronometers available to geologists, allowing them to date the formation of oceanic crust with accuracies approaching 10,000 years across time spans of 200 million years. The chemistry of the spreading ridge basalts reflects the composition of the upper mantle as it undergoes decompression, melting beneath the diverging plates. The magmas that create Atlantic oceanic crust show characteristic signatures of mid-ocean ridge volcanism, with low concentrations of incompatible elements and isotopic ratios that indicate derivation from relatively depleted mantle sources. Occasionally, the spreading ridge encounters mantle plumes rising from much greater depths, creating oceanic islands like Iceland, where the interaction between ridge spreading and plume volcanism generates unusually thick oceanic crust with distinctive chemical characteristics. The sedimentary blanket that accumulates on the aging oceanic crust records the environmental history of the Atlantic basin as it widens and deepens over hundreds of millions of years. The oldest sediments, deposited when the ocean remained narrow and relatively shallow, consist primarily of carbonates and evaporates that indicate warm, tropical conditions across much of the basin. Later sediments include deep-sea clays and turbidites that reflect the establishment of true oceanic depths and the development of continental margin sedimentary systems as the surrounding landmasses evolved their characteristic drainage patterns. Only took 200 million years to fill an ocean with stories written in mud. The seafloor observes with satisfaction at the accumulating historical record. The development of oceanic circulation patterns within the growing Atlantic fundamentally alters global climate by creating new pathways for heat transport between low and high latitudes. The early Atlantic lacks the complex current systems that characterize the modern ocean, instead developing simple gyre patterns that gradually become more sophisticated as the basin widens and the surrounding continental configurations evolve. The opening of deep water connections between the Atlantic and other ocean basins proves particularly important for global thermohaline circulation, creating opportunities for the formation of deep water masses that sink in polar regions and flow equatorward along the ocean floor. The continental margins that border the growing Atlantic evolve through a predictable sequence of structural and sedimentary phases as they adjust to their new role as passive margins rather than sites of active tectonism. The initial rift-related topography gradually subsides as the lithosphere cools and contracts, creating broad continental shelves that become sites of extensive carbonate platform development during periods of high sea level. These passive margin sequences preserve detailed records of relative sea level change, climate evolution, and the biological innovations that occur as marine ecosystems adapt to the new oceanic environments. The fracture zones that offset the mid-Atlantic ridge create some of the most prominent topographic features on the ocean floor, forming linear valleys and ridges that extend for thousands of miles across the abyssal plains. These transform faults accommodate the slight changes in spreading direction that occur as the ridge adjusts to the complex three-dimensional geometry of plate motion, creating characteristic stair-step patterns in the ridge crest that reflect the mathematical constraints imposed by motion on a spherical surface. The transform faults themselves become sites of distinctive geological processes, including serpentinization reactions that alter the chemical composition of the oceanic lithosphere and create unique habitats for deep-sea biological communities. The hotspot tracks that cross the Atlantic Ocean floor record the motion of the spreading ridge and the overlying plates relative to deep mantle plumes that remain relatively stationary over geological time. The most prominent of these tracks extends from the Deccan Traps through the Mascarene Islands to the modern position of the Réunion hotspot, documenting the northward motion of the Indian Ocean spreading system as it separated from Africa. Similar tracks in the Atlantic record the complex dance between ridge migration and plate motion that characterizes the evolution of spreading systems over hundreds of millions of years. Scientists studying the Atlantic's opening face the challenge of reconstructing precise plate motions from the sometimes contradictory evidence preserved in magnetic anomalies, fracture zone orientations, and hotspot tracks. Computer models that simultaneously satisfy all available constraints reveal a complex history of changing spreading rates and ridge reorganization events that reflect the evolving forces driving plate motion. Some periods show steady, symmetric spreading, while others record dramatic changes in spreading direction or rate that coincide with major reorganizations of global plate motions. The biological evolution of the Atlantic basin proceeds in parallel with its physical development, as marine organisms adapt to the changing environmental conditions and develop new biogeographic patterns as the ocean widens. The early Atlantic supports relatively simple marine ecosystems dominated by organisms adapted to warm, shallow water conditions, while the later development of deep water environments creates opportunities for the evolution of specialized deep-sea faunas. The increasing separation between the Atlantic's eastern and western margins gradually reduces genetic exchange between marine populations, leading to the evolution of distinct biogeographic provinces. The influence of Atlantic opening on global tectonics extends far beyond the immediate effects of seafloor spreading, as the creation of new oceanic lithosphere in the Atlantic requires the consumption of oceanic crust elsewhere to maintain the planet's overall surface area. This consumption occurs primarily in the Pacific Ocean, where subduction zones around the Pacific Rim gradually reduce the size of the Pacific Basin as the Atlantic expands. The seesaw relationship between Atlantic opening and Pacific closure represents one of the fundamental constraints on global plate tectonics over the past 200 million years. The Atlantic continues its patient breathing today, adding new oceanic crust at the spreading ridge while the continental margins drift ever farther apart, carrying with them the geological and biological heritage of their former connection within Pangaea. The ocean that began as a narrow rift valley has evolved into one of Earth's major ocean basins, demonstrating the planet's capacity for fundamental reorganization over the vast timescales of geological processes. Each breath of the spreading ridge adds another few centimeters to the ocean's width, continuing the process that will eventually carry the continents to configurations unimaginable from any modern perspective, until the forces that drive continental drift finally reorganize themselves once again into patterns that favor convergence rather than divergence. India's long journey north begins as a fragment breaking away from the supercontinent Gondwana with all the deliberate patience that characterizes continental drift, separating from Antarctica and Australia along spreading ridges that will operate for more than 100 million years before the subcontinent finally collides with Asia. The Indian plate starts its northward odyssey as a triangular piece of continental crust roughly the size of modern Alaska, carrying within its ancient rocks the geological memory of southern polar climates and the distinctive flora and fauna that evolved during Gondwana's long existence as a unified landmass. This wandering piece of Pangaea embarks on one of the most remarkable journeys in the history of plate tectonics, traveling more than 6,000 miles across the ancient Tethys Ocean at speeds that occasionally reach 20 centimeters per year. Unusually fast by the standards of continental drift, the mechanism driving India's rapid northward motion remains one of the most intriguing puzzles in plate tectonic theory. As the subcontinent moves significantly faster than most other continental fragments during comparable periods of Earth's history, some geophysicists propose that a large mantle plume beneath the Indian Ocean provides additional driving force through thermal buoyancy and active upwelling, while others suggest that the unique geometry of the spreading ridges surrounding the Indian plate creates particularly efficient coupling between mantle flow and plate motion. The Deccan Traps, massive volcanic outpourings that cover much of western India with layers of basalt up to 2 miles thick, provide evidence for intense mantle plume activity during the later stages of India's journey, though the relationship between this volcanism and the plate's rapid motion remains uncertain. The Tethys Ocean that India crosses during its northward journey represents one of the largest seaways in Earth's history, a tropical sea that extends from the western Mediterranean region through Central Asia to the Pacific Ocean, creating a circumglobal belt of warm, shallow water that supports diverse marine ecosystems and influences global climate patterns. As India travels across this ocean, it encounters a series of microcontinents, island arcs, and oceanic plateaus that gradually accumulate along its northern margin through collision processes that serve as previews of the much larger collision that awaits when the subcontinent finally encounters the Asian mainland. Each of these smaller collisions adds exotic terrains to India's leading edge, creating a complex geological collage that preserves evidence of the subcontinent's long journey. The sedimentary rocks deposited on India's continental margins during its transoceanic voyage record the changing environmental conditions encountered as the subcontinent drifts from high southern latitudes through the tropics toward the northern subtropics. Early Cretaceous sediments include glacial deposits and cool water carbonates that formed when India lay close to the South Pole, while later deposits consist of tropical reef complexes and warm water limestones that accumulated as the subcontinent crossed the equator and entered the northern hemisphere. These paleoclimatic indicators provide some of the most compelling evidence for continental drift, demonstrating that landmasses have indeed moved vast distances across the Earth's surface over geological time. The oceanic crust that forms behind India as it separates from Gondwana preserves a detailed magnetic record of the subcontinent's motion, creating stripe patterns that allow scientists to reconstruct its path with remarkable precision. The magnetic anomalies reveal that India's motion includes several significant changes in direction and velocity, including a period of very rapid northward movement during the late Cretaceous and early Paleogene periods that coincides with the eruption of the Deccan Traps. These velocity changes reflect modifications in the forces driving plate motion, possibly related to changes in mantle convection patterns or the initiation of new subduction zones along India's trajectory. Only took 50 million years to cross an ocean the size of the modern Pacific. Geological time notes with admiration for such efficient continental transportation. The biological cargo that India carries during its journey includes distinctive assemblages of plants and animals that evolved during the subcontinent's isolation from other landmasses. The breakup of Gondwana occurs during a crucial period in the evolution of flowering plants and mammals, allowing these groups to diversify independently on the separating continental fragments. India's biota develops unique characteristics during the subcontinent's oceanic voyage, creating endemic species that will later contribute to the biological diversity of Asia when the collision finally occurs. The fossil record preserved in Indian rocks provides important evidence for biogeographic evolution during continental drift. The subduction zones that consume the oceanic crust in front of India's northward-moving leading edge operate with the mechanical efficiency characteristic of convergent plate boundaries, recycling the Tethyan seafloor back into the mantle while simultaneously creating volcanic arcs and accretionary complexes along the southern margin of Asia. These subduction systems generate some of the largest earthquakes in Earth's history as they accommodate the convergence between India and Asia, while the associated volcanic activity creates mountain ranges and plateau regions that will later be incorporated into the collision zone when India finally arrives. The progressive closure of the Tethys Ocean as India approaches Asia creates increasingly restricted circulation patterns that influence regional and global climate evolution during the Mesozoic and early Cenozoic eras. The shrinking seaway becomes less effective at transporting heat between ocean basins, while the growing topography associated with the approaching collision begins to influence atmospheric circulation patterns across Central Asia. These paleoclimatic changes provide important boundary conditions for understanding the evolution of global climate systems during the transition from greenhouse to icehouse conditions. The deep structure of the Indian plate reveals evidence for the unique conditions that enabled its rapid northward motion, including an unusually thick lithospheric root that may have provided additional gravitational driving force through its negative buoyancy. Seismic studies of the modern Indian Ocean show that the plate retains some distinctive characteristics that differentiate it from typical oceanic lithosphere, possibly reflecting its origin as a fragment of the Gondwana supercontinent rather than as purely oceanic crust formed at spreading ridges. The timing of India's collision with Asia remains one of the most intensively studied problems in Himalayan geology, with different lines of evidence suggesting collision ages ranging from about 55 to 35 million years ago. The uncertainty arises partly from the complex, multi-stage nature of the collision process, which begins with the accretion of various microcontinents and island arcs to the Asian margin before the main Indian continental mass finally arrives. The definition of collision itself proves problematic when applied to processes that unfold over tens of millions of years and involve the complex interaction between multiple crustal blocks. The approach trajectory that brings India into collision with Asia determines many aspects of the subsequent mountain-building process, including the distribution of deformation, the style of crustal thickening, and the pattern of river systems that will develop to drain the growing mountain ranges. Computer models of the collision process must account for the complex three-dimensional geometry of the converging margins, the rheological properties of the continental crust involved in the collision, and the influence of erosion and climate on the evolving topography. India's long journey north concludes not with a single dramatic impact, but with a complex, multi-stage collision process that continues today, nearly 50 million years after the initial contact between the continental margins. The subcontinent carries with it the geological and biological heritage of Gondwana, introducing southern hemisphere rocks, fossils, and isotopic signatures into the Asian continent while simultaneously undergoing fundamental transformation through the mountain-building processes that create the modern Himalayas and Tibetan Plateau. The journey demonstrates the remarkable capacity of plate tectonics to transport entire continents across ocean basins, reorganizing the global distribution of land masses over geological time while preserving within the transported crust detailed records of the environments and conditions encountered during the voyage. Mountains rise from collision grain by grain, crystal by crystal, as India crashes into Asia with continent crumbling force that operates so slowly no human observer could detect its progress without the most sensitive instruments. The impact unfolds over tens of millions of years, transforming two separate landmasses into a single continent marked by the highest peaks on Earth and a plateau so vast it influences weather patterns across the entire northern hemisphere. The Himalayas and the Tibetan Plateau emerge from this collision like geological flowers blooming in extreme slow motion, each mineral grain climbing toward the sky at rates measured in millimeters per decade, while erosion races against uplift in a contest that will continue until the forces driving the collision finally exhaust themselves. The initial contact between the Indian and Asian continental margins occurs not as a single dramatic event, but as a complex process of accretion involving multiple microcontinents, island arcs, and oceanic plateaus that get caught between the converging land masses like geological filling in a continental sandwich. These exotic terrains, originally formed in various parts of the Tethys Ocean, become welded to the Asian margin through collision processes that serve as previews of the much larger mountain-building episode that follows when the main Indian continental mass finally arrives. Each accretion event adds geological complexity to the collision zone, creating a mosaic of rock types and structures that preserves evidence of the ocean basin's complex history. The mechanics of continental collision differ fundamentally from the subduction processes that consume oceanic crust, because continental rocks are too light and buoyant to sink into the mantle even under the enormous pressures generated by plate convergence. Instead of disappearing into the Earth's interior, the continental crust involved in the collision must accommodate the convergent motion through some combination of crustal thickening, lateral escape, and surface uplift. The Indian continental margin responds to the collision by developing a complex array of thrust faults that stack slices of crust on top of each other like geological playing cards, doubling or even tripling the original thickness of the continental lithosphere. The Tibetan Plateau represents perhaps the most remarkable consequence of the India-Asia collision, creating a high-elevation region larger than Alaska that averages more than 15,000 feet above sea level across an area that could contain the entire continental United States. This plateau forms through a combination of crustal thickening and thermal expansion that raises the land surface to elevations where the atmosphere becomes too thin for most forms of life to survive without adaptation. The plateau's formation requires the involvement of both the Indian and Asian continental crusts, with some models suggesting that Asian crust flows laterally away from the collision zone like toothpaste squeezed from a tube, while others propose that the entire thickened crustal mass rises as a coherent block. The Himalayan mountain range forms along the southern edge of the collision zone, where the leading edge of the Indian plate meets the thickened Tibetan crust, creating a linear belt of peaks that includes all 14 of the world's mountains higher than 8,000 meters. These peaks rise through a combination of thrust faulting that carries older rocks over younger ones, and normal faulting that drops the highest parts of the range relative to their surroundings in a gravitational response to the extreme topography. The mountains grow through the complex interplay between tectonic uplift and erosional downcutting, with rivers like the Ganges and Indus carrying away billions of tons of sediment each year, while the peaks continue rising faster than erosion can wear them down. Only took 50 million years to build the roof of the world. The patient collision observes with understated pride in this achievement of geological engineering. The deep structure of the collision zone reveals evidence for processes operating at depths of hundreds of miles beneath the surface, where the Indian continental lithosphere appears to be sliding beneath the Asian plate in a process sometimes called continental subduction. Seismic studies show that pieces of the Indian plate extend to depths of at least 200 miles beneath the Tibetan plateau, suggesting that significant portions of the Indian continent have been buried beneath Asia during the collision process. This deep burial occurs despite the buoyancy of continental crust, because the mechanical coupling between the Indian and Asian plates generates forces sufficient to drag continental material to depths where it would normally be unstable. The metamorphic processes operating within the collision zone create some of the most extreme pressure and temperature conditions ever documented in continental crust, transforming ordinary sedimentary and igneous rocks into exotic mineral assemblages that can only form under the conditions of extreme crustal thickening. These ultra-high-pressure metamorphic rocks preserve mineral relics that indicate burial to depths of 60 miles or more before being returned to the surface through subsequent erosion and tectonic exhumation. The presence of these rocks provides direct evidence for the recycling of surface materials deep into the collision zone and their eventual return to the surface through processes that operate over millions of years. The climatic consequences of the India-Asia collision extend far beyond the immediate vicinity of the mountain range, influencing weather patterns across Asia and contributing to the establishment of the monsoon circulation systems that bring seasonal rainfall to billions of people. The Tibetan Plateau acts as a massive heat source during summer months, warming the overlying atmosphere and creating low-pressure systems that draw moisture-laden air inland from the surrounding oceans. During winter, the plateau becomes a cold, high-pressure zone that generates the dry continental air masses that characterize Asian winter weather. These seasonal circulation patterns develop gradually as the plateau rises, fundamentally altering the climate evolution of the entire region. The erosional products of the collision zone create some of the world's largest sedimentary systems, as rivers draining the Himalayas and Tibetan Plateau carry enormous quantities of debris to the surrounding ocean basins. The Ganges-Brahmaputra Delta system builds outward into the Bay of Bengal at rates of several miles per million years, while the Indus River creates massive submarine fans that extend hundreds of miles into the Arabian Sea. These sedimentary systems preserve detailed records of the collision's progress, with changes in sediment composition and accumulation rates reflecting the evolving topography and climate of the source regions. The ongoing nature of the India-Asia collision means that the mountain-building process continues today, at rates that can be measured using modern geodetic techniques, including GPS positioning and satellite interferometry. These measurements reveal that the Himalayas continue rising at rates of several millimeters per year, while simultaneously moving northward as the Indian plate maintains its inexorable push into Asia. The collision zone remains one of the most seismically active regions on Earth, generating frequent earthquakes that accommodate the ongoing convergent motion and remind observers that the mountain-building process remains far from complete. The biological consequences of the collision prove equally dramatic, as the rising mountains create new habitats and migration barriers that influence the evolution and distribution of plants and animals across Asia. The Himalayas serve as a biogeographic barrier that separates the tropical flora and fauna of the Indian subcontinent from the temperate species of Central Asia, while the high-elevation environments of the Tibetan Plateau support specialized communities adapted to extreme cold and low atmospheric pressure. The timing of mountain building relative to major evolutionary radiations influences which groups of organisms achieve widespread distributions and which remain restricted to particular regions. The collision between India and Asia demonstrates the remarkable power of plate tectonics to reshape continents and reorganize global geography over geological time, transforming an oceanic region into the highest mountains and largest plateau on Earth through the patient application of forces that operate below the threshold of human perception. The process continues today with undiminished vigor, adding millimeters to mountain heights and pushing the collision zone ever deeper into the Asian continent, writing new chapters in the geological story with the same methodical persistence that has characterized continental drift since the earliest days of plate tectonics. The Pacific Ring shrinks with each passing millennium as the ancient ocean basin contracts around its perimeter like a vast puddle slowly drying under the patient influence of geological time. While the Atlantic Ocean learns to breathe and expand, the Pacific surrenders its ancestral territory to the advancing continental margins that encroach from all directions, consuming oceanic crust along subduction zones that operate with the mechanical precision of planetary recycling centers. This contraction occurs so gradually that the Pacific remains Earth's largest ocean basin even after 200 million years of steady shrinkage. Yet the cumulative loss amounts to thousands of miles of seafloor that once stretched between continents, now much closer to each other than their Pangaean ancestors could have imagined. The ring of fire that encircles the Pacific Ocean marks the active boundaries where oceanic lithosphere plunges back into the mantle, creating chains of volcanoes and zones of seismic activity that extend for thousands of miles around the ocean's perimeter. These subduction zones operate like conveyor belts in reverse, carrying old oceanic crust down into the Earth's interior at rates of several centimeters per year, while simultaneously generating the magmas that build volcanic mountain ranges and island arcs along the overriding plates. The volcanic activity proceeds with characteristic geological patience, each eruption adding infinitesimal amounts to the growing mountain chains, while the slow consumption of oceanic crust continues relentlessly beneath the surface. The Andes Mountains rise along South America's western margin as the Nazca Plate slides beneath the continental crust, generating one of the longest and highest mountain chains on Earth through processes that have operated continuously for more than 100 million years. The volcanic arc that forms above the subducting oceanic lithosphere creates peaks that rival the Himalayas in elevation while extending for more than 4,000 miles along the continent's Pacific coast. The mountains grow through the accumulation of volcanic rocks and the compression of the continental margin, creating a complex blend of igneous and metamorphic processes that build continental crust grain by grain while the oceanic plate disappears into the mantle below. The island arcs that characterize much of the western Pacific Ocean represent some of the most volcanically active regions on Earth, with chains like Japan, the Philippines, and Indonesia forming, where oceanic plates subduct beneath other oceanic plates rather than beneath continental margins. These intraoceanic subduction zones create linear archipelagos of volcanic islands that rise from the deep ocean floor like stepping stones across the vast Pacific basin. Each island in these chains represents millions of years of volcanic accumulation, growing from the seafloor through repeated eruptions that gradually build edifices capable of emerging above sea level and supporting terrestrial ecosystems. The deep ocean trenches that mark the sites of active subduction create some of the most extreme topography on Earth's surface, forming linear depressions that plunge to depths exceeding 35,000 feet below sea level. The Mariana Trench, deepest of these features, descends farther below sea level than Mount Everest rises above it, creating pressure conditions at its bottom that exceed those found anywhere else on the planet's surface. These trenches form where the down-going oceanic lithosphere bends as it begins its descent into the mantle, creating flexural depressions that trap sediments eroded from the surrounding volcanic arcs and continental margins. Only took 100 million years to dig the deepest holes on Earth. The subduction zones note with satisfaction at their excavation efficiency. The earthquake activity associated with Pacific subduction zones generates some of the most powerful seismic events in recorded history, including the Great Chilean Earthquake of 1960 and the Tohoku earthquake that triggered the devastating tsunami in Japan in 2011. These megathrust earthquakes occur when stress accumulated over centuries of slow plate convergence releases suddenly along the interface between the subducting oceanic lithosphere and the overriding plate, generating ground motions and tsunami waves that can affect coastlines thousands of miles from the earthquake source. The earthquake cycle operates with predictable regularity over timescales of hundreds to thousands of years, though individual events remain difficult to forecast with precision. The transform faults that connect different segments of the Pacific Ring create additional pathways for accommodating the complex motions required as the ocean basin contracts. The San Andreas Fault System represents the most famous of these features, accommodating the northward motion of the Pacific Plate relative to North America through a combination of strike-slip faulting and distributed deformation across a zone several hundred miles wide. These transform systems create their own distinctive types of seismic activity and topographic features, including the linear valleys and offset stream channels that mark the active fault traces. The hotspot volcanic chains that cross the Pacific Ocean floor record the motion of the oceanic plates over deep mantle plumes that remain relatively stationary over geological time. The Hawaiian Emperor Seamount chain provides the most complete example of such a hotspot track, with the bend in the chain marking a dramatic change in Pacific plate motion that occurred about 50 million years ago. These volcanic lineaments serve as valuable recorders of plate motion, allowing scientists to reconstruct the changing directions and velocities of Pacific plate movement over the past 100 million years with remarkable precision. The sedimentary cover on the Pacific Ocean floor preserves evidence for the environmental changes that have accompanied the basin's contraction, including the effects of changing ocean circulation patterns and climate evolution. The thick sedimentary sequences found in some parts of the Pacific record tens of millions of years of oceanic sedimentation, preserving within their layers evidence for past climate changes, volcanic activity, and biological evolution. These deep-sea sediments provide some of the most complete records available for understanding long-term environmental change, though much of this record eventually disappears into subduction zones as the oceanic crust carrying the sediments gets recycled into the mantle. The biological evolution of Pacific ecosystems responds to the changing geography created by the basin's contraction, with new migration routes opening and closing as volcanic islands emerge and submerge, and as continental margins shift their positions relative to each other. The complex topography of the Western Pacific, with its numerous island arcs and marginal seas, creates opportunities for isolation and speciation that contribute to the region's exceptional biological diversity. The Ring of Fire serves as both a barrier and a pathway for biological exchange, depending on the timescales and organisms involved. The mineral resources associated with Pacific subduction zones include some of the world's most important deposits of copper, gold, and other metals that form through hydrothermal processes operating in volcanic arc environments. The circulation of seawater through hot volcanic rocks creates chemical conditions that concentrate these metals into ore deposits that will later be exposed by erosion and tectonic uplift. The Pacific Ring of Fire thus serves as a major source of the mineral resources that human civilization depends upon, though the same tectonic processes that create these deposits also generate the volcanic and seismic hazards that threaten human populations. The future evolution of the Pacific Ocean basin depends on the continued operation of the subduction systems that currently consume oceanic lithosphere faster than new crust forms at the East Pacific Rise and other spreading centers within the basin. Computer models of long-term plate motion suggest that the Pacific will continue shrinking for hundreds of millions of years into the future, eventually becoming a much smaller ocean basin as the Americas approach Asia and Australia. This long-term contraction represents part of the supercontinent cycle that may eventually lead to the formation of a new Pangea-like landmass, though the details of this future continental assembly remain highly uncertain. The Pacific Ring continues its patient work of oceanic contraction today, consuming seafloor along subduction zones while generating the volcanic and seismic activity that reminds observers of the ongoing forces that reshape the Earth's surface. Each earthquake and volcanic eruption around the Pacific perimeter represents a small increment in the basin's long-term evolution, contributing to processes that will eventually transform the geography of the entire planet through the same patient persistence that has characterized plate tectonics since continental drift first began billions of years ago. Present motion. Future drift carries the continents through their current configurations toward destinations that exist only in the mathematical projections of plate tectonic models, each landmass following trajectories determined by forces operating deep beneath the surface, with the same patient persistence that has driven continental movement for billions of years. Africa inches northward into Europe at rates of a few millimeters per year, gradually closing the Mediterranean Sea and building the alpine mountain ranges grain by grain through collisions that unfold over millions of years. Australia continues its northward journey toward Asia, carrying its unique cargo of marsupial life across oceanic gaps that shrink imperceptibly with each passing millennium. The Atlantic Ocean widens by several centimeters annually, while the Pacific contracts at similar rates, redistributing the planet's water across ocean basins that will bear little resemblance to their current configurations when measured against the vast timescales of geological transformation. The modern GPS networks that track continental positions with millimeter precision reveal that the Earth's surface remains as restless today as it was during any period in the geological past, though the movements occur at speeds that require sophisticated instruments to detect across human lifespans. North America drifts westward relative to Europe at about the same rate that human fingernails grow, while South America rotates slowly counterclockwise as it separates from Africa along the mid-Atlantic ridge. These contemporary motions continue the same processes that assembled and dispersed Pangea, demonstrating that continental drift represents not a historical curiosity, but an ongoing planetary phenomenon that will continue reshaping global geography for billions of years into the future. The driving forces behind present-day continental motion remain fundamentally the same as those that have operated throughout Earth's history: though their relative importance shifts as the planet's internal heat production gradually declines through radioactive decay. Mantle convection continues to provide the primary driving mechanism, with hot material rising from the deep interior and spreading laterally beneath the lithosphere before cooling and sinking back toward the core. The convection patterns that drive current plate motions reflect the cumulative effects of billions of years of thermal evolution, creating circulation systems that operate with the efficiency born of geological experience. The earthquake activity that accompanies contemporary continental motion provides direct evidence that the forces driving plate tectonics remain vigorous despite the planet's advanced age. The great subduction zone earthquakes that periodically devastate coastal regions around the Pacific Ring of Fire release energy that has accumulated over centuries of steady plate convergence, while transform fault earthquakes like those along the San Andreas system accommodate the lateral motion between adjacent plates. These seismic events operate as safety valves for the enormous stresses generated by continental drift, preventing the accumulation of forces that might otherwise tear the continents apart or lock them in place. The volcanic activity associated with modern plate boundaries continues to build new continental crust while simultaneously recycling older material back into the mantle, maintaining the dynamic balance between creation and destruction that has characterized the Earth's surface throughout geological time. The mid-ocean ridges generate new oceanic lithosphere at rates carefully calibrated to match the consumption of old oceanic crust at subduction zones, while continental volcanic arcs add material to the landmasses through processes that operate with the same methodical persistence displayed by their ancient predecessors. Only took 4 billion years to perfect the art of continental maintenance. The modern Earth observes with characteristic understatement about this achievement in geological engineering. The climate consequences of ongoing continental drift continue to influence global environmental patterns through their effects on oceanic and atmospheric circulation. The gradual closure of oceanic gateways between continents alters the pathways available for heat transport between different parts of the ocean system, while the growth of mountain ranges modifies atmospheric circulation patterns on regional and global scales. These changes occur so slowly that they remain invisible to human observation, yet they accumulate over geological time into transformations that fundamentally alter the planet's climate system. The biological implications of continuing continental drift extend far beyond the immediate effects of changing geography, influencing evolutionary processes through the creation of new barriers to dispersal and new opportunities for isolation and speciation. The ongoing separation of South America from Africa continues to drive the independent evolution of their respective biotas, while the gradual approach of Australia toward Asia creates opportunities for biological exchange that will eventually transform the ecosystems of both continents. These biogeographic changes operate on timescales that dwarf human history, yet they represent the continuation of processes that have shaped the distribution of life on Earth since complex organisms first evolved. The deep structure of the continents preserves evidence for their complex histories of assembly, dispersal, and reassembly through multiple supercontinent cycles, with the oldest rocks recording events that occurred more than 3 billion years ago. The Canadian Shield, Siberian Platform, and other ancient cratonic regions represent the stable cores of the continents, built through processes of collision and accretion that operated according to the same principles governing modern continental drift. These ancient terrains serve as geological libraries that preserve detailed records of conditions on the early Earth, though much of this record remains difficult to interpret due to the extreme age and complex history of the rocks involved. The future trajectory of continental drift depends on the continued operation of mantle convection driven by the planet's internal heat sources, though the gradual decline in radioactive heat production will eventually lead to changes in the style and vigor of plate tectonics. Computer models of long-term thermal evolution suggests that plate tectonics may continue operating for another billion years or more, though at gradually decreasing rates as the driving forces weaken. The exact timing of this transition remains uncertain and depends on poorly understood aspects of mantle dynamics and the feedback mechanisms that couple surface tectonics to deep Earth processes. The supercontinent cycle that has characterized Earth's evolution for billions of years appears likely to continue into the future, with the scattered fragments of Pangaea eventually reassembling into a new supercontinent through collision processes similar to those that created their predecessors. Various models propose different configurations for this future supercontinent, ranging from scenarios where the Atlantic closes and the Americas collide with Europe and Africa, to alternatives where the Pacific closes and Asia approaches the Americas. The uncertainty reflects the complex, non-linear nature of the plate tectonic system and the sensitivity of long-term predictions to small changes in current conditions. The technological revolution that has allowed precise measurement of contemporary continental motion represents one of humanity's greatest achievements in understanding the planet's operation, providing direct confirmation of theories that were purely speculative just decades ago. Satellite-based positioning systems, interferometric radar, and other space-based technologies now track continental positions with accuracies that surpass the precision of any previous geological observations, revealing details of plate motion that would have been impossible to detect using traditional methods. The economic implications of ongoing continental drift extend to virtually every aspect of human civilization, from the distribution of mineral resources created by ancient tectonic processes to the seismic and volcanic hazards that threaten modern infrastructure. Understanding the long-term trajectories of continental motion provides crucial information for assessing the future availability of resources and the evolving patterns of geological hazards that will affect human societies for generations to come. Present motion continues with the same patient persistence that has characterized continental drift since the Earth first developed a solid crust capable of movement, carrying the continents toward futures that will unfold over timescales so vast that they challenge human comprehension. Each millimeter of annual motion represents a small step in journeys that will eventually transform the planet's geography as completely as the assembly and breakup of Pangaea transformed the world that existed 300 million years ago, demonstrating the Earth's inexhaustible capacity for change across the infinite patience of geological time. Deep time's endless patience reveals itself most completely in the story of continental drift, where the pace of transformation operates according to rhythms so slow that mountains rise and fall, species evolve and vanish, and entire ocean basins open and close within what amounts to single breaths in the planet's geological respiration. The Earth demonstrates through its wandering continents a capacity for change that dwarfs human imagination, while simultaneously displaying a persistence that makes the most enduring human achievements seem momentary. 4 billion years of continental motion unfold like a vast, slow symphony, where each movement lasts hundreds of millions of years. Each theme develops across geological eras, and the entire composition continues playing long after any audience capable of hearing it has evolved, flourished, and disappeared into the fossil record. The timescales that govern continental drift exist beyond the normal boundaries of human comprehension, requiring mental stretches that challenge the capacity of minds evolved to navigate daily and seasonal cycles rather than geological epochs. A single supercontinent cycle, from assembly through stability to breakup and dispersal, spans periods longer than the entire history of complex life on Earth, yet represents merely one movement in a dance that has repeated multiple times since the planet first developed solid crust capable of movement. The continents perform this dance with the patience of stone, each step measured in millions of years, each gesture extending across distances that encompass entire hemispheres. The forces that drive continental drift operate with the reliability of physical law, neither hurrying toward completion nor pausing for rest, but maintaining their steady influence across time periods that reduce entire geological eras to brief episodes in a much larger narrative. Mantle convection continues its work with mechanical precision, circulating heat from the planet's interior to its surface through currents that flow for hundreds of millions of years without deviation, creating the thermal engine that powers continental motion with fuel derived from radioactive decay processes that operate according to half-lives measured in billions of years. The Earth's internal heat production decreases so gradually that its effects become noticeable only across periods that span significant fractions of the planet's entire history. The rock record that preserves evidence of continental drift extends back nearly to the beginning of Earth's solid crust formation, creating a geological library where each page requires millions of years to write and each chapter spans entire geological periods. The stories written in stone record not just the positions of ancient continents, but the environmental conditions they experienced, the climates they endured, and the life forms they supported during their slow journeys across the globe. These records reveal a planet in constant motion despite its apparent stability, where the solid ground beneath observers' feet participates in movements so gradual they remain invisible across thousands of human generations. The mathematics of continental drift operate according to equations that balance forces acting over geological timescales, where velocities measured in centimeters per year accumulate into displacements spanning thousands of miles, and accelerations so small they approach zero. Nevertheless, produce dramatic changes in continental configurations over sufficient time. The precision required for continents to follow predictable paths across such vast periods, while responding to forces that vary continuously, demonstrates a level of systematic organization that emerges from the complex interactions between multiple physical processes operating simultaneously across different scales of space and time. The continental fragments that wander across Earth's surface carry within their crystalline structure memories that extend back billions of years, preserving in their mineral compositions and isotopic ratios records of conditions that prevailed when the solar system itself was young. These geological memories survive multiple episodes of continental drift, collision, and dispersal, creating archives of Earth history that remain accessible to scientific investigation despite having participated in planetary processes of almost incomprehensible complexity and duration. The continents serve as both actors and chroniclers in their own epic journey, writing their experiences into the rocks that compose their substance. The biological consequences of continental drift unfold over timescales that encompass the entire history of life on Earth, influencing evolutionary processes through mechanisms that operate so slowly their effects become apparent only when viewed across millions of generations. The separation and reunion of continents create and eliminate migration routes, establish and remove barriers to gene flow, and generate the geographic isolation necessary for speciation processes that require geological time to complete. The distribution of life on the modern Earth bears the signature of continental positions that existed tens or hundreds of millions of years ago, demonstrating the profound influence of geological processes on biological evolution. Only took 4 billion years for the continents to learn biogeography. Deep Time notes with satisfaction at this integration of geological and biological processes. The future evolution of continental drift extends indefinitely into a future so distant that the Sun itself will undergo fundamental changes before the process concludes. Yet, the mechanisms that drive continental motion show no signs of approaching exhaustion even after billions of years of operation. The planet's internal heat sources remain adequate to power mantle convection for periods that exceed the remaining lifetime of the Sun, suggesting that continental drift will continue until external factors rather than internal exhaustion bring the process to an end. The eventual fate of continental motion depends on the long-term evolution of the entire solar system, rather than any limitations inherent in the Earth system itself. The cyclical nature of continental drift suggests that the planet operates according to rhythms that transcend any particular configuration of land and sea, creating patterns that repeat over timescales so vast they approach the periodic variations observed in astronomical phenomena. The supercontinent cycle represents one manifestation of these deep rhythms, assembling and dispersing the continental fragments according to schedules that reflect the fundamental timescales of mantle convection and thermal evolution. These cycles demonstrate the Earth's capacity for self-organization across periods that dwarf human history, while maintaining coherent patterns that persist across significant fractions of the planet's total age. The philosophical implications of continental drift challenge conventional notions of permanence and stability, revealing that even the most apparently solid and enduring features of the planet participate in constant transformation across timescales that render them ephemeral when viewed from the perspective of deep time. The continents that seem so fixed and immutable from human perspectives prove to be temporary arrangements of crustal material that will eventually disperse and reassemble in configurations as different from the present as the present differs from ancient Pangaea. The unity underlying continental drift emerges from the recognition that all parts of the Earth system participate in the same fundamental processes, driven by the same energy sources and governed by the same physical principles that operate with equal effectiveness across all scales of space and time. The wandering continents demonstrate the deep connections that link surface geology to interior dynamics, local topography to global climate, and biological evolution to physical processes, revealing the Earth as an integrated system where no component exists in isolation from any other. Deep Time's endless patience continues its work today with the same measured persistence that has characterized geological processes since the planet first acquired solid crust capable of movement, carrying forward the story of continental drift toward chapters that will unfold over periods so vast they transform the very concept of duration into something approaching eternity. The continents continue their wandering across the patient Earth, writing new pages in the geological record with the same methodical persistence that has filled libraries of stone with the accumulated wisdom of 4 billion years of planetary experience, demonstrating through their endless journey the capacity of matter and time to create beauty, complexity, and meaning through nothing more than patient persistence across the vast expanse of geological duration. The story of continental drift settles into stillness, like sediment drifting toward the ocean floor, each grain finding its resting place in the vast accumulation of geological time. The continents continue their patient wandering even now, moving beneath sleeping cities and dreaming forests at speeds too slow for any lifetime to perceive, yet fast enough to reshape the entire planet across the deep rhythms that measure Earth's breathing. In this moment of quiet, the mountains pause in their imperceptible rising, the oceans rest in their slow expansion and contraction, and the ancient stones carry forward their billion-year memories with the silence that comes from knowing time without end. The dance of drifting lands flows onward through darkness and light, through seasons that last for millions of years, and climate changes that unfold like chapters in a book written by the planet itself. Each fragment of continent bears within its crystalline heart the story of journeys that began when the world was young and molten, carrying those memories forward into futures so distant they exist beyond imagination. The Earth turns in its ancient rhythm, neither hurrying toward any destination nor pausing for any observer, but simply continuing the motion that began when the first solid ground appeared on a cooling world. In the depths beneath all restlessness, The mantle continues its eternal circulation, rising and falling in currents that will persist until the sun grows cold and the oceans boil away into space. These deep rivers of stone flow with patience that transforms mountains into sand and sand into stone again, writing and rewriting the surface of the world with the persistence of geological love. The continents rest upon these currents like dreams upon sleep, carried forward through time by forces that operate beyond all urgency, beyond all haste, in the perfect stillness that lies at the heart of all motion. The wandering lands find their rest not in any final destination, but in the eternal present of their movement, each moment of drift containing within itself all the journeys that came before and all the transformations yet to come. In this geological peace, time itself becomes a kind of sleep, where billions of years pass like single breaths, and the patient earth continues its ancient work of becoming, grain by grain, breath by breath, in the infinite quiet of deep time's endless dreaming.